All right, let's talk about something you hear about constantly. Large language models, or, LLMs. But what's really going on under the hood? Well, today we're going to break down how they actually work. We'll go from something as simple as your phone's keyboard all the way up to the most powerful AI on the planet. Okay, let's just dive right in. It really all starts with a simple question. One you've probably experienced 100 times. You're typing a message, right? And your phone just knows the next word you want to use. So how does it do that? Well, believe it or not, you're looking at a super basic version of the exact technology we're going to explore today. So at its very core, that autocomplete feature, that's a language model. Its entire job is just to predict what comes next. And this is a really key point. It's not understanding you. Think of it more like a super sophisticated pattern matching machine. It's been trained on just mountains of text to make the best possible guess. Okay, let's make this a little more concrete. Look at the sentence here. When I hear rain on my roof, I blank in my kitchen. So what a language model does is it analyzes this whole sequence of words and then tries to figure out the most probable word to fill in that blank, all based on the patterns it's seen before. And this is where it gets really interesting. You can see how the model breaks down the probabilities. It calculates that cook soup has about a 9.4% chance. Warm up a kettle is sitting at 5.2%, and so on down the list. The model isn't thinking about what it's like to be cozy on a rainy day. No, it's just playing the odds. It's like a really high-stakes guessing game based on all the text it's ever seen. All right, so that pretty much explains a simple language model. But what happens when we make it large? I mean, what's the real difference between just predicting one little word and generating a whole essay? Let's take a look at how that complexity really builds up. I mean, the jump in capability it's staggering, seriously. Early models, they were limited to predicting just the next word. That's it. But today's large language models, they can generate entire sentences, paragraphs, even whole documents. The scale has just absolutely exploded. So how do we even measure this largeness? Well, we use something called parameters. And a great way to think about parameters is like they're millions, or in some cases billions, of little internal knobs and dials that the model gets to fine-tune during its training. The more of these knobs it has, the more complex and nuanced the patterns it can learn to recognize. It's funny, just a few years ago, a model called BERT was considered massive. And it was. It had 110 million parameters, which was a huge leap at the time. It allowed it to recognize way deeper language patterns than anything that came before it. But now, look at this. Modern models like Palm 2 can have up to 340 billion parameters. That's not just a step up, it's a completely different universe of scale and complexity. And this massive increase is exactly what unlocks their most incredible abilities. But how did we make that incredible leap? It wasn't just about throwing more data or faster computers at the problem. No, a key architectural breakthrough was needed to handle all that information effectively. And this is where the transformer comes in. So back in 2017, a research paper introduced the transformer architecture, and it just completely changed the game. Its secret weapon was this amazing mechanism called attention. And what that did was allow models to process really long sequences of text without, losing the plot. It solved a major hurdle that had plagued all the earlier design. Right. And at the very heart of the transformer is this idea of self-attention. Now, for every single word it processes, the model essentially asks itself, okay, how important is every other word in this sentence to me? And by doing that over and over, it builds this complex web of relationships and really starts to grasp the context of the entire passage. Let's look at a quick example. Here's a sentence. The animal didn't cross the street because it was too tired. Seems pretty simple for us humans to understand, right? But for a machine, there's a real ambiguity here. What does the word it actually refer to? Is it the animal or is it the street? We know this intuitively, but a machine has to figure it out by looking at the connections between all the words. And this is what brilliantly illustrates the power of self-attention. The mechanism weighs all those connections, and it determines that it is strongly linked to animal. And why? Well, because it's learned a simple statistical pattern. Animals get tired, streets don't. It's this incredible ability to resolve ambiguity that gives these LLMs their deep contextual grasp of language. It's pretty amazing. Okay, so this power to understand context unlocks some absolutely incredible new abilities. But as you can probably guess, with that great power comes some pretty significant challenges and, of course, responsibilities. Now, what's truly mind blowing is that as these models get larger and larger, new skills just sort of appear. They aren't explicitly programmed to do things like summarize articles or write code or solve math problems. These are called emergent abilities, and they're a direct result of just operating at such a massive scale. It's what makes them so incredibly versatile. But all this power, it's really just the tip of the iceberg. What we don't often see are the huge challenges lurking right beneath the surface. I'm talking about the sheer scale of resources and engineering that's required to make these things work in the first place. Yeah, there are some major considerations here. First, the cost. It's immense. Training these models can take months and consumes just enormous amounts of energy. Then there's the engineering. It's incredibly complex, and it requires all this special hardware and programming. And maybe most importantly, there are the issues of bias and ethics. Remember, these models learn from a giant snapshot of the internet, so they can absolutely reflect and even amplify the human biases that are already out there. Things related to race, gender, you name it. So where does all of this leave us? Well, we have this unbelievably powerful new tool that is evolving at a breakneck pace, and the path forward is going to require a really careful balancing act. Ultimately, it really just comes down to this. Progress can't be the only goal. As these models become more and more a part of our world, our responsibility to understand and to deal with their drawbacks has to grow right alongside their capabilities. The two have to go hand in hand. And that, of course, leaves us with the big question that we all need to start thinking about. As these large language models become a fundamental part of our daily lives, everything from simple autocomplete to really complex decision-making, how do we, as a society, make sure they are built and used in a way that is fair, that is safe, and that is truly beneficial for everyone?